Dust control and the possibility of eradicating silicosis in underground mining with mechanized transport. Authors: Efrain Bozo Godoy, mechanical civil engineer from the University of Santiago de Chile, and Gonzalo Bozo Nally, mechanical civil engineer from the Technical University Federico Santa Maria. Both specialists in material management and dust control. Part 1: Silicosis, Particulate Matter, State of the Art and Recommendations for Suppression and Humidification. More than 60 years ago, the ILO recognized that pneumoconiosis and silicosis were one of the most serious and costly occupational hygiene problems that industry has to deal with, and perhaps the most difficult to resolve. Considering sadly harsh data, such as deaths from silicosis per 100,000 inhabitants, we see that in South America, a mining continent, no progress has been made in eradicating silicosis. Chile is the leader in this reality. And at that time, dry haze already existed. The question is there any possibility of eradicating silicosis by 2030? It is very likely that in 2030 and in 60 years we will still be using the same methods. As Albert Einstein said, insanity is doing the same thing over and over again and expecting different results. Important concepts: respirable crystalline silica. Silica is the respirable fraction, PM5, less than 5 microns, of crystalline silica or silicon dioxide, the most abundant element in nature. Silicagenic environment is one that has 1% or more of silica. People exposed to this environment can acquire silicosis in a few weeks or years, depending on the concentration of silica. Silicosis is an irreversible and progressive pulmonary fibrotic disease, considered a disabling occupational disease, which takes years to detect. The COMET diagram, prepared from a Zender study for turbulent and hurricane-force winds, shows that the 5-micron particle needs a wind speed of less than 0.02 km per hour to remain suspended. PM5 is therefore considered non-sedimentable, and is released in grain reduction, polishing, combustion, etc. In open-pit mining, the main sources of PM5 release and contamination are drilling and blasting, by far the largest source of respirable silica, crushing processes, and grinding processes. Silica is released in comminution processes, which reduce the grain size. In underground mining, the main source of PM5 release and contamination is drilling and sinking. The other processes are similar to those in open-pit mining. It should be noted that the PM5 that does not go into the environment remains trapped in the mineral itself or adhered to larger slag deposits or agglomerated with other fines, being a sure and potential contaminant downstream. And what happens in a transfer between conveyors? To understand the phenomenon in any transfer, we need to know the physical concept of induced air. That is, the falling material opens and leaves gaps with negative pressure or vacuum, which are filled with absorbed air. When the material impacts, it releases all this air that we call induced air. That is, in a discharge without confinement, the induced air is equal to all the air absorbed during the discharge. There is no equation to estimate the induced air without confinement or with wide confinement, hoppers or domes. We have developed a mathematical model that was selected by ASME as an innovation for AMES 2024. Induced air is present in all bulk material transfers. In a transfer between conveyors, if a mathematical model is available, the most important and most widely used is that of Dr. David Anderson. His equation shows that when the induced area is reduced, part of the induced air recirculates, decreasing the air to be extracted. Sealing the induced area together with sealing the sidewall is what is known as passive dust control. Passive control is mandatory in all transfers if you want to successfully avoid fugitive dust. The most widely used method for dust control is suppression: air, water, mainly dry mist. In dust suppression we have 4 stages, each with its own efficiency. These are collision between particle and drop of similar size. It is of the Brownian type, random in nature. agglomeration of successful collisions or with particles of larger diameter. Reception on the surface of the belt material. If the speed of the fall limit is lower than the speed of the belt, it will not be deposited or will not adhere to the surface. Maintenance. After reception, at the exit of the sieve, the relative speed is higher. Therefore, unstable particles will go into the environment. The total efficiency is given by the multiplication of the four efficiencies. The results show that this system, by itself, is too inefficient. When passive control is efficient and is complemented by active dust control, the result is successful. Not only on site, but downstream. Active control with water or water-air nozzles performs three functions, which are: curtain to promote sealing and recirculation of dust, surface wetting to fix the particles to the hoppers, suppression or abatement of particles. The curtain allows for recirculation that gives more time to promote abatement. This mixed control, passive control plus active control. It is efficient for local control and contributes to dust control downstream. Wetting all the material or applying water indiscriminately has only one advantage. It reduces visible dust. And it has the following disadvantages. It does not reduce PM5 or PM10 and, therefore, silica continues to be present in the environment. It increases the accumulation of dust on the floor. It impairs the segregation and fluidity of the material in hoppers, stockpiles, and piles. The wet material adheres to mechanical and structural components. It complicates the cleaning of the belt. The detachment of particles from the surface is not controlled. For all the above reasons, this method does not contribute to the control of PM5 or PM10. It is not recommended. More than 15 kilometers of belts, whose speed is 7 meters per second, to transport approximately 11,000 tons per hour. There are significant concentrations of PM10, PM5, and silica. Dust is not apparently visible. However, particles of up to 400 microns can be released from the surface of the belt. There is a lot of dust on the floor because the speed in the tunnel is low. Surface wetting on the surface of the material on a conveyor belt allows the surface of the coarse mineral that is positioned on top to be wetted. It has the following advantages. It promotes the adherence of the fines on the hoppers, including PM5. It prevents particles from being released from the surface of the material. In the next transfer, more fines will adhere to these wet surfaces. It reduces segregation by distributing the fines in mineral stockpiles. It improves fluidity or mass flow in hoppers, stockpiles, and piles. Therefore, surface wetting of the material is a method that must be present in the efficient control of dust and silica. Surface wetting with foam is a good solution. However, care must be taken with the surfactant, which complicates recovery in some processes. Part 2. State-of-the-art and recommendation for extraction. Innovation for the final elimination of PM10. One of the forms of dust control is extraction, which aims to capture the dust generated in the mining process and prevent its release into the work environment. One type of extraction is high-speed extraction, which NIOSH defines as when the transport speed exceeds 15 meters per second. This high-speed system is the most widely used in the mining industry. However, transport speeds of over 20 meters per second are used, and even over 25 meters per second. In a hood, the capture speed ranges between 1 and 1.5 meters per second and works for laminar flow. Inside a hood, the flow is turbulent and the capture speed is defined by the speed of the vertical duct adjacent to the hood, which can transport particles of 2 millimeters or more. High conveying speed causes significant wear on ducts due to constant abrasion of large dust particles. This wear is especially critical in areas where the airflow changes direction, such as at bends and branches, which can lead to the formation of holes and cracks in the ducts, affecting the integrity of the system. This is the main failure with risk of collapse. This disadvantage not only affects the operational efficiency of the system, but also increases maintenance costs due to continuous critical failures and reduces the useful life of the equipment, representing a considerable challenge for mining operations. Another fault with a higher risk of high-velocity system collapse is the settling of fines in horizontal duct runs, especially under high humidity conditions or when airflow is insufficient. This situation is aggravated during emergency or maintenance shutdowns, when airflow stops and allows dust to settle. The resulting dust buildup increases resistance to airflow, decreases system efficiency, and can cause partial or total blockages in the ducts. If not properly managed, these conditions will lead to complete collapse of the dust extraction system. This disadvantage not only affects the operational efficiency of the system, but also increases the costs of maintenance or ongoing cleaning of the ducts, provided that gates have been considered to allow this cleaning. To avoid the disadvantages of the high-velocity system, NIOSH proposes the modified low-velocity system, which consists of taking advantage of the high-velocity system while avoiding its main disadvantages. The key to the success of the modified low system lies in the design of the capture hood and the first section of the duct. In the modified low-velocity system, the first section of the duct must be vertical for at least 6 feet, preferably between 8 and 10 feet, to reduce turbulence, achieve a smooth laminar flow, and optimize elutriation, which is the separation of lighter particles from heavier ones. The velocity in this initial vertical section is low, between 1,000 and 1,200 feet per minute, allowing only the finest particles to be transported through the duct. After this vertical rise, since there are few particles in the airflow, it is not necessary to maintain high velocities in the horizontal runs. The velocity in the first horizontal run should be approximately 2,000 feet per minute, which is sufficient to transport the smallest respirable particles to the dust collector without the need for complex designs or intermediate discharge points. Another important consideration in the design of MLV systems is that as additional lateral lines are connected to the main trunk line, the trunk line exit velocity should be increased by approximately 100 feet per minute after each lateral connection. Despite this, even on long runs with many lateral connections, the line velocity upon reaching the collector is unlikely to exceed 2,500 to 3,000 feet per minute. Modified low-velocity system offer the following advantages: extracts less dust and smaller particles. By capturing mainly finer particles, the MLV reduces the amount of dust transported through the duct, which decreases abrasion and therefore reduces the need for frequent maintenance. Eliminates risk of collapse. By maintaining adequate flow rates and avoiding the accumulation of material in the ducts, the modified low-velocity system minimizes the risks of blockage and collapse of the system. Does not detach particles adhered to the culpas during capture. In previous processes, the wetting of the material can cause fine particles to adhere to the culpas. The modified low-velocity system, unlike the high-speed system, does not detach these particles during capture, improving dust control. Consumes less energy, because it captures and transports less dust at a lower speed and due to the optimized design of the system, reducing operating costs due to its high availability. Normally in the industry, after dust extraction it is returned downstream. All this dust will be raised again by the speed of the belt or in the next transfer. So what do we do with the dust, including PM5 and silica? One of the most promising options to solve this problem is dry granulation. This method is considered an innovation in the mining sector, although it has already been used in other industries as an effective method for dust control. Dry granulation allows fine dust to be captured and transformed into larger, more manageable granules, thereby reducing dust dispersion in the environment and improving air quality. By returning dust in the form of granules, not only is the recirculation of contaminants in the mining process avoided, but an economic benefit is also obtained, since this dust has a higher mineral grade compared to the general material. With this technique, a global option for dust control is offered, effectively solving the challenges associated with dust contamination in mining, while maximizing the use of the captured material. In this video, We observe a part of the dry granulation process in the pharmaceutical industry, where the powder is turned into flakes by a roller compactor. The roller compactor compresses the fine powder under pressure, turning it into flakes. In a further process, called granulation, these flakes will be turned into granules. However, in mining, we are satisfied with leaving the powder in the form of flakes, which is sufficient to reduce the dispersion of the dust in the environment and improve material handling. Some applications of granulation in other industries are EAF, electric arc furnace dust. Electric arc furnace dust, a byproduct of the steel industry containing metals such as zinc, lead and iron, is granulated to allow for its safe and efficient recycling, reducing the dispersion of dust into the environment. Food. In the food industry, granulation facilitates the handling of ingredients, minimizing the generation of dust during processing and storage. Drugs. In the pharmaceutical industry, granulation is essential for the manufacture of tablets and capsules, reducing the generation of dust in the production process. Fertilizers. Granulation in the production of fertilizers allows the creation of uniform particles, reducing the generation of dust during handling and storage. Granulated slag. Blast furnace slag is granulated for use in cement and concrete manufacturing, reducing dust emissions during processing. Coal briquettes. Granulation converts coal dust into briquettes, reducing dust generation during handling and use. At the Transbelt 2023 Congress, Francisco Cabrejos of Genike and Johansson presented a similar alternative for dust management in mining. His proposal focuses on returning dust to the process in more manageable forms, such as glomerates, pellets, briquettes, or compact tablets. In addition, Cabrejos highlighted the importance of studying the need to apply additives during the granulation process to improve the cohesion and stability of these compact forms, thus ensuring more effective dust management in mining operations. Following this line of research, Genike and Johansson conducted laboratory tests using specialized equipment to manufacture compact pellets. In these tests, they were able to convert mining dust into compact pellets, demonstrating the viability of this technique as an effective solution for dust control in mining environments. These tests allow them to evaluate the effectiveness of the process and the possibility of implementing this technology on a larger scale in mining operations. Another study conducted by the Institute of Mineral Processing Machines focused on the agglomeration of fine coal dust using a disc granulator, with the aim of improving coal handling and transport, reducing dust emissions and the risks associated with dust explosions. Laboratory tests demonstrated that coal dust can be transformed into larger, more manageable agglomerates, as seen in the figures showing fine and coarse grains. These agglomerates significantly improve the flow and transport properties of the coal, and can be reintegrated into the process or sold as quality fuel, thus increasing the economic value of the coal originally in dust form. Let's close with a quote from Abraham Maslow: "When the only tool you have is a hammer, every problem begins to look like a nail." The dust control problem has us trapped in a cycle where we continually look for a definitive solution in existing tools that have proven not to be sufficient to solve the problem. That is why I invite you to dare to try something new and solve the dust control problem. Thank you very much for your attention.